So we are going to talk about the basic concepts of the ABM, and these concepts are very much important. So watch the video till end, and also you can be enrolling into the crash course of the CAIIB, where we'll be covering each and everything in just very short manner, and definitely you can succeed with very good marks, at least 60%. I'm assuring you that. So just follow the link in the description, or you can simply be WhatsApping us CAIIB English crash course and WhatsApp to the number given below, that is 8360944207. So let's start the session here. So first of all, it's related to the different type of the events. So let's do consider that there are two different events, and event is actually a subset of the complete space. So we're considering we are having the events A and the event B over here, and these two events are said to be the mutually exclusive event if these two events cannot happen together. Let's just suppose you just tossed a coin. Either it will be a head or it will be a tail. It cannot be both of it, right? And it can also be neither of it. So it's basically like either the head will come up or the tail will come up. So these are both mutually exclusive events. That's the first type of it. Second one, it's related to the exhaustive events. Now, in the case of the exhaustive events, when two events will basically be occurring or more events will be occurring, they will all be covering all the other possible events in the particular outcomes. So when two or more events occur and they do cover the complete sample space, that is said to be the exhaustive events. Now these can be represented by A union B is equal to the complete sample space. And the first one, that is a mutually exclusive events, this can be specified like A intersection B is equal to 5 means empty space, nothing will come up, right? Now the third type over here, that is actually related to the complementary events, when one event is actually the exact opposite of the same, and the probability of those two basically conclude to one, because we know the value of the probability varies from 0 to 1. So if I'm saying if A is complement of the other, so it will be represented as plus PA dash, that will basically be equal to 1. The complete probability range will be covered into it. That means these are complementary events. Fourth one, it's related to equally likely events. When every outcome is having a fair chance so as to appear, that is said to be the equally likely events. Like you basically roll the dice and every face of the dice is having the equal probability to come up. Those are said to be equally likely events. So far, we have learned a few concepts related to the types of events. Like for equally likely event, I told you then you basically roll a dice. Every single face is having the equal chance so as to appear. That is equally likely event. For the complementary event, it's related to odd and even like, and both will be comprising the complete sample space. For exhaustive events, when two events will be concluding or more events will be concluding, they will be concluding to the complete sample space, that is exhaustive events. And when we're talking about the mutually exclusive events, it means the two events which cannot happen together, those are said to be the mutually exclusive events. There are some other event types too. Let's understand them. Like some events are like certain events mean it will happen and definitely these outcomes will come. Like when you roll a dice, you are basically pretty much sure that something between 1 to 6 will come. Now these are said to be the certain events. And what do you mean by the impossible event? When you know it cannot come, like the probability of getting 7 on a die, it's not possible at all, so it's impossible event. That's the other type of it. So I'm just writing over here, that is impossible events. Now let's learn four theorems based on the probability. First theorem that we are going to learn, it's the addition theorem. Let's do consider there are two events A and B. So the probability of A will be equal to this and probability of B will be something like this. And if I say what is the probability of P, A or B, it means we are talking about the probability of A plus probability of B, and what's the common part that is to be subtracted, right? So it will be P A intersection B, right? That is to be subtracted. Now how come we are basically calculating this? Just draw these diagrams. Let's say this is indicating probability of A, this is indicating probability of B. When we are adding them up, this particular point space, which is the intersection between these two, that will be come up twice. So we subtracted the one part, right? So this is how probability of A and B will come up. And if these two events are mutually exclusive, in that scenario, P A intersection B will be equal to 5. So it will come if events are mutually exclusive. In that scenario, P A union B is equal to probability of A plus probability of B. That's it. If these are mutually exclusive, because I told you above that if the events are mutually exclusive, in that scenario, there will be no common space. So those will be something like this: A and B. There is no intersection between them, right? That is the addition theorem. In the case of the conditional probability, we are having something like this, like probability of A and B has already happened, and this is represented like A divided by B. So in this case, we are to calculate the probability of, keeping in mind that the event B has already occurred. Now, in that scenario, it is equal to the probability of A intersection B divided by the probability of B, keeping in mind the probability of B is having a value which is greater than 0, right? So this is mathematically like probability of A divided by B, probability of event A that B has already occurred, that is equal to probability of A intersection B divided by the probability of B. But now let's try to get this point through an example, because many times the questions are going to be asked based upon this particular theorem directly. So let's consider the case that you are having a bag of balls, and here we are having three red balls and we are having two blue balls. So we are having in total five balls in the bag. So let's suppose the case that we just drew one ball from the bag and kept it aside, right? That is the scenario. And after that, now we are going to draw another ball. So we drew first ball and kept it aside, and then we'll be drawing the second ball. Now it may be the scenario that the first ball may be a red ball, or it may be the case that it is a blue ball, right? Now, if we work upon the same, we can say the probability of B when we are considering, let's say, the first ball is the red ball, right? And for the second scenario, we are considering the A, which we are saying the ball drawn is a blue ball. Now, what will be the probability of B here? The probability of B that we are having three red balls. So it will be like 3 divided by the total number of events, that is total number of events over here, balls over here, that is equal to 5, right? Not actually event, it will be the total number of the elements in the sample space, right? So it will be equal to 5, because from the three balls we are to select the one ball, so it will be 3C1 divided by the 5C1, because one ball out of 5 is to be selected, right? So it will be 3 divided by 5. And if we are to calculate the intersection between these two, that the ball is drawn and the first ball was a red ball, and if we have to calculate the probability of the second one, we have to basically calculate the intersection between the two, so as to use the theorem over here, right? We'll be multiplying the two events, probability of A multiplied by the probability of B. The probability of event B we already have calculated, it is 3 divided by 5. So it will be 3 divided by 5. But what about the probability of A? Because second ball drawn can be a red ball or it can be a blue ball, right? And in that scenario, we are to pick, if we are saying, because we considered that the second ball is a blue ball, so we are in total having the 5 balls, but we have already picked one ball. Now we are left with 4 balls, right? So in denominator, we'll be having 4 and we are having two blue balls, so the probability of this will be equal to 2 divided by 4. So it will be equal to 3 by 5 and multiply by 2 by 4. Is that clear? So it will be equal to 3 divided by 10. So what will be the probability like? Probability of A that B has already occurred. We'll be saying like this. Why? Because the red ball is already drawn, and now we want to calculate the probability of event A. Now what is the probability for the same? It is a probability of A intersection B divided by the probability of B here. So we calculate the A intersection B, it is 3 divided by 10, and further 3 by 5 for the probability of B, right? So it is equal to 1 divided by 2. This is the answer that we are getting over here, right? So what kind of question will be asked? They will be asking you what is the probability of getting the second ball as a blue ball if the first ball is a red ball, right? So in that scenario, we know that the event B has already occurred and we have to calculate for the event A here, right? So we'll be using this formula, that is A intersection B divided by the probability of B. But keep in mind, the probability of B must be greater than 0 must be having a positive value, right? So we learned about the additional theorem, we learned about the conditional probability. Now the third one, it's related to the multiplication theorem. And the next theorem we are going to talk about, it's related to the multiplication theorem. When we're talking about the multiplication theorem, it means we want to calculate the probability when both of the events will occur. So it's like probability of A and B, right? So if we're talking about A and B, it means probability of A and further multiplied by the probability, conditional probability that A has already occurred. Now A has already occurred, so probability of B that A has already occurred, something like this, or it is equal to probability of event B multiplied by probability of event A that B has already occurred, right? And in case if these are independent events, these are not dependent, right? So if the case is there that these are independent events, in that scenario probability of B divided by A, it will not be affected by the probability of A, so this will be equal to probability of B here. And if we talk about the probability of A that B has already occurred, so that will be equal to probability of A here. So this will become equal to probability of multiplied by probability of B, and the second one will become equal to probability of B multiplied by probability of A. In what scenario? These two scenarios are there if these two are independent events. Otherwise, the probability will be equal to A and B will be equal to probability of A multiplied by probability that event A has occurred and the probability of B upon that, right? So these were the four theorems I was talking about. So we covered the additional theorem, we covered the conditional probability, we covered the multiplication theorem, and also the independent events. So I hope that you must have liked the video. So if you like the content, do give this a thumbs up. And if you want me to cover more numerical problems related to the independent events and the multiplication theorem, do write yes in the comment sections and I'll be posting the video super soon. So that will be all. And as I told you, the crash course is available. Just do enroll. Each and everything is covered over there in detail. So that will be all related to this video. Thank you so much and see you again in the next video.